So we've seen that we can add vectors, and we've seen that we have this way of multiplying a vector with a scalar, right? We called that the scalar product. We wrote it like this. So that kind of prompts the question, is there a sensible way to multiply vectors? Your first guess might be just to say, well, look, addition of vectors and scalar products of vectors just happen component by component, so shouldn't we do the same thing to multiply vectors? So if we have a vector v that's v1, v2, v3, and a vector w that's w1, w2, w3, then maybe we should define a product, which I'm calling star for my own reasons. Shouldn't we define this product to just be v1, w1, v2, w2, v2 times w3, v3 times w3? This seems like a perfectly sensible way to define multiplication of two vectors. But remember, one of the key things about addition and scalar multiplication is that even though we can write addition and scalar multiplication for vectors in terms of coordinates, the way that they're actually defined is in terms of some kind of intrinsic geometry having to do with vectors that we think of as arrows, right? So let's see what happens geometrically if we use this product. So I'm going to write this a little differently. Well, you'll see why we need to do this in a second. So v1, v2, v3. This is the vector v1i plus v2j plus v3k. Right, so I'm using our standard basis vectors I, j, and k. And so w is going to be w1i plus w2j plus w3k. Okay, so this product would be v1 w1i plus v2 w2j plus v3 w3 times k. Okay. So let's look at a particular example. Right? Let's look at a particular example. And the example that we're going to use, I'm going to draw this example, and then we'll sort of express it in terms of I, j, and k. Actually, we're going to stick to 2 dimensions for this, so we won't actually need our third terms here. Okay, so for us, v is going to just be the vector I, like this. So here's v. I need to put my vector hat on things. The vector w for us is just going to be j, like this. So there's w. Okay, now we can write what happens when we do v star w, right, this product that we made up. So this is, right, v is kind of playing the role of 1, 0, and w is playing the role of 0, 1, kind of. So, right, we get 1 times 0 times I plus 0 times 1 times j. So that's the 0 vector, right? So when we did this computation using our standard basis I and j, we got the 0 vector. But the whole point of vectors is that they have the whole point of vector operations is that they should have independent geometric meaning even if you change the coordinate system. So let's keep these same 2 vectors, v and w, and remember their unit length. I'm not writing that down, but remember that they're unit length. And this time, let's say that our coordinate system is like this. Okay, so this means we have a new unit vector pointing in the positive x direction. Calling that I might be confusing, so let's call it A for now. And we have a new unit vector pointing in the positive y direction, and let's call that B for now. So to work out what is v star w, we need to express v and w in terms of these 2 vectors, right? Our basis vectors kind of serve as the building blocks for all other vectors. So let's express v and w in terms of a and b. So it turns out that you have to do some trigonometry. This angle here is pi over 4, by the way, or minus pi over 4. So you have to do some trigonometry to express v in terms of a and b, but I'll spoil the surprise and just write down what you get. So v turns out to be 1 over root 2 times a plus 1 over root 2 times b. Hopefully this is plausible that, right, this 1 over root 2 and this 1 over root 2, those are coming from the sine and cosine of pi over 4, right, because pi over 4 is there. I'll let you work out the trigonometry on the details. For w, w is minus 1 over root 2 a plus 1 over root 2 b. Okay, it makes sense that a minus sign should show up here because we kind of, in the a direction, we kind of have to back up to get w. So that's why this minus sign shows up. And so now let's work out what is v star w in this other coordinate system. Well, remember, the way that we've defined this product, you just multiply corresponding entries. So for our a entry, we get 1 over root 2 times minus 1 over root 2. That's minus a half. So minus a half a plus, and then 1 over root 2 times 1 over root 2. So 1 over 2 times b. But this is not the 0 vector, right? So if we used our original coordinate system, this product gave us the 0 vector. And if we use this other coordinate system, it didn't give us the zero vector. So what this is saying is, whatever this product is calculating, it doesn't have any geometric meaning that is independent of the coordinate system. And so, independent of the orientation of the coordinate system. And so this product is not useful for us. This is not how we will define the multiplication of, or the product of vectors. Okay, so it will be tempting maybe for you to use this product in the future, but this is not what we will be using, just because it doesn't mean anything geometrically. Now, if you study enough other technical fields, like especially data processing fields or data analysis fields, often they will use vectors as just a convenient way to describe a list of numbers, and the numbers are data values. And sometimes in those contexts, you do need to multiply corresponding entries like this. But when we're talking about vectors as geometric objects, which is what we are doing, this product doesn't mean anything. So put this out of your minds for now.